Deutsch algorithm is the very first quantum algorithm that indicates that quantum computers could be more powerful than classical computers. It was first published by David Deutsch in his 1985 paper. In this video, we shall explain the math behind the Deutsch algorithm and show that the code for Deutsch algorithm in Cirq and Qiskit. The problem of Deutsch algorithm can be formulated as follows. First, we have a classical function that maps 0, 1 to 0, 1. So the problem that we want to solve is f0 equal to f1? And if f0 is equal to f1, we say f is a constant function. And if f0 is not equal to f1, then we say f is a balanced function. First, we will need to convert a classical function to a quantum function, which must be reversible and unitary. And this quantum function is commonly known as the oracle. So this is how we construct an oracle function. We have a unitary matrix over here. We have two inputs. So the first output will be the same as the first qubit, and the second output for the second qubit will be given by y plus f on x. So let's see that this is a reversible by reverse the direction of the operation. So x, y plus fx will get x again here, and the y plus fx will be plus fx, and this is just 0, right? Because 0 plus 0 or 1 plus 1, and we will get y plus 0, and we get y. So the Deutsch algorithm can be implemented by this circuit. First, we have two qubits. The first qubit is 0 and the second qubit is 1, and both of them go through the Hadamard operation and fit into the oracle. And we perform a Hadamard on the first qubit output and do a measurement. If the measurement is 0, we infer that this function is a constant function. And if the measurement is 1, then we infer that this function is a balanced function. In order to understand the math, we look at 3 checkpoints: psi 1, psi 2, and psi 3. So psi 1 is after the Hadamard operation, which give us plus and minus, and we expand out the plus, we get 0 plus 1 over square root 2, cancel with minus, so we get 0 minus and plus 1 minus. So as psi 2 is after the oracle function, so we apply oracle on this and this, we'll get to this and this. Now we need to evaluate this. Let's look at this configuration. X and input y is minus, and we'll get x and y minus plus fx, right? Which is these two terms here. And this minus we can expand onto this 0 minus 1, and due to the dissociation property, we can write 0 plus f and 1 plus f, and 0 plus f is just none other than f, and 1 plus f we can write 1 minus f. The reason can be seen over here. So when fx is 0, we get 1 plus 0 is equal to 1, which is equal to 1 minus 0. If fx is 1, we get 1 plus 1, will give us 0, which is 1 minus 1. So now we can write the quantum state of the output as x fx and x1 minus x. And this can be further put in a more concise form as minus 1 to the power fx x minus. Let's see why. So when fx is 0, we got x 0, x 1 minus 0 is 1, and we can combine the last the second qubits to minus. And when fx is 1, we got x 1 and x 1 minus 1 is 0, and this is just a reverse of the first one, so it's minus x minus minus. So we can write in this more concise form. So when 0, we get to this. When it's 1, we get a negative sign here. So now side 2 can be written as minus 1 f0 0 minus and minus 1 f1 1 minus. So now we have two possible scenarios, f0 equal to f1. So when both are equal, we can bring out this term, which is over here, and then we can see that we left with 0 minus and 1 minus, and we can combine the first qubit into plus. When f0 is not equal to f1, this is not equal to this, then we end out there's a negative sign here or the negative sign here, and then we can bring out this one. We either end up with a plus here or minus here, but we will get 0 minus minus 1 minus, and then we can combine the first qubit into minus minus. So now look at side 3, which is after the Hadamard. The Hadamard will convert this plus to a 0 and minus to a 1. So side 3 will be equal to 0 when f0 is equal to f1, and equal to 1 when f0 is not equal to f1. So if we take the measurement, we'll get 0 for the constant case and 1 for the balanced case. This completes the math behind the Deutsch algorithm. We shall now go and look at the code in Cirq and Qiskit. So let's look at the Cirq first. We import the Cirq. We define two qubit Q0 and Q1. So we apply the Hadamard on the first qubit and followed by X and H on the second qubit. Then we have three possible oracle, the balance, where we can use a C0 to do the balance function, or we can have constant 0 and constant 1. Constant 0 is none other than just do nothing, and constant 1 we can implement using a XK. And after the oracle, we need to apply a Hadamard on the first qubit and do the measurement on the first qubit. And then we go through the simulator and we look at these three possible oracles and run 10 times each time. And indeed, when we see that when it's balanced, we always get 1. When it's constant, we always get 0, and it's constant 1, we also always get 0. Let's look at Qiskit. We import all the libraries, and then we define a quantum circuit, and we apply a H on the first qubit, X and H on the second qubit, and then we have three possible oracles: balance, constant 0 and constant 1. And then after the oracle, we apply a Hadamard on the first qubit and do the measurement. And then we go through the simulator again. We see that when it's a balance, we always get 1. When it's constant, we always get 0, regardless it's constant 0 or constant 1. Right? That concludes the video for Deutsch algorithm. The code can be downloaded below. If you like to feedback on the video, We welcome your comment below. If you like this video, please share and subscribe to our channel. Thank you.